Hello, this is Dr. VC Sontake and I am going to take the course Heat Transfer. The objectives of this video lectures are: number one, to explain the concept of hydrodynamic or velocity boundary layer in internal flow. Number two is to explain the concept of thermal boundary layer in internal flow. And last objective is to explain their significance in forced convection heat transfer during internal flow. So let us first define what do we mean by internal flow. So whenever the fluid flow is taking place through a confined passage like pipe, tube, it is called internal flow. The cross-section of the pipe through which fluid flow is taking place may be either circular or rectangular or square shape. Nature of internal flow. Whenever fluid is flowing through a pipe, tube or any constricted passage, depending upon the velocity of the fluid, the flow may be either laminar or turbulent. So the nature of internal flow, whether it will be laminar or turbulent, is determined by calculating Reynolds number represented by Re suffix d is equal to rho u infinity Lc over mu is equal to u infinity Lc over nu. Here the symbol Re suffix d is used to represent the Reynolds number in case of internal flow. We have discussed in case of external flow, the Reynolds number is represented by Re suffix L, where the L represents the linear dimension in case of external flow, because fluid is flowing over a linear dimension in case of external flow. Similarly, in case of internal flow, the suffix d represents either the internal diameter or internal dimensions. So please bear this notation of Reynolds number in case of external flow, that is Re suffix L, and in case of internal flow, that is Re suffix D. In the above equation, Lc is called as characteristics length or significant length. Mu is dynamic viscosity in Pascal second, and nu is kinematic viscosity in meter square per second. Generally, for internal flow, the characteristics length is taken as hydraulic diameter dh, and it is calculated by the formula 4AC by P. In this formula, the AC is the cross-sectional area of the passage through which the fluid is flowing, and P is its perimeter. Now, depending upon the value of Reynolds number calculated, flow will be laminar if value of Reynolds number is less than 2300. Flow will be in transitional zone if Reynolds number lies between 2300 and 10,000, and flow will be turbulent flow if Reynolds number is greater than 10,000. Now, as we have discussed, characteristics length in case of internal flow is taken as hydraulic diameter calculated by 4AC by P. Now, depending upon the cross section of the pipe or tube, hydraulic diameter may vary. For example, for circular tube of internal diameter D, the hydraulic diameter can be calculated as dh is equal to 4 into cross-sectional area of this pipe will be pi by 4 d square by 4 over its perimeter will be pi d. So hydraulic diameter for circular tube of diameter d is taken as equal to its diameter capital D. For any square duct of side A, hydraulic diameter dH is equal to 4A square over 4A, and that comes out A. So for square duct of side A, hydraulic diameter will be its equal to one of its side A. And for rectangular duct of dimensions A and B, hydraulic diameter will be 4A AB over twice A plus B is equal to twice AB over A plus B. So for rectangular duct of side A and B, hydraulic diameter comes out twice AB over A plus B. Now let us come to very important phenomena, that is boundary layer development in case of internal flow. So in case of internal flow, like external flow, there are two types of boundary layer development. The number one is development of velocity or hydrodynamic boundary layer, and this takes place due to no slip conditions. And development of thermal boundary layer, and this is developed due to no temperature jump conditions. The concept of no slip condition and no temperature jump condition have been discussed in detail in earlier videos. So kindly refer those videos in case of external flow. So let us start our discussion of development of hydrodynamic or velocity boundary layer. In short, it is called as VBL for a fluid flowing through tube, and particularly the nature of flow is laminar. So let us consider a tube represented here having diameter capital D. It is having sufficient length through which fluid is flowing. Let us consider the fluid with free stream velocity u infinity is entering into this tube. So at the entrance of this tube, the velocity profile shape will be uniform and constant. Now let us consider some sections 0A, 0B, 0C, and the last section 0D. Now at a distance of x from the entrance of this pipe, let us say at section 0A, because of no slip condition, whenever a fluid is flowing through the stationary pipe, the velocity of the fluid particle in contact with the stationary pipe surface comes to 0, because velocity of the pipe wall is also 0. This condition is called as no slip condition. That is, whenever a fluid is flowing over an stationary surface, its velocity, the particle of that velocity, the velocity of that particle, sorry, will also becomes equal to the surface velocity. In this case, it is 0. So similarly, in this case, velocity of the fluid particle at the bottom surface and at the top surface will become 0. Now, the velocity of the particle flowing or sliding over this stationary particle will get reduced due to friction or viscous forces from u infinity to some reduced value. Similarly, the velocity of the another particle which is flowing over this particle will get reduced from free stream velocity u infinity to some reduced velocity. So what happens actually As a result of this no slip condition, velocity of the fluid varies from 0 at the surface to the free stream at the center line of this tube. And since there are two stationary surfaces in case of pipe flow, top surface and bottom surface, this velocity variation will be observed in the bottom direction as well as in the upper direction. That is, velocity gradient will be existing in top side and in bottom side. So as a result of this, velocity profile is having different velocities varying from top surface to the center line, similarly from bottom surface to the center line. Now the distance y, at a distance y, the velocity gradient is existing. The velocity is 0 at the top surface and velocity is equal to 99% of the free stream velocity, and this distance is called as velocity boundary layer thickness. As we move away from the inlet of this pipe in the x direction, the effect of this no slip condition is observed or is penetrated more in the y direction, and because of which velocity boundary layer thickness is growing. So what happens actually, because of this no slip condition, velocity gradient is existing and its thickness is increasing as we move away from the entrance of the pipe. So this region in which velocity gradient is existing is called as velocity boundary layer. So in case of internal flow or flow through the pipes, velocity boundary layer formation will be taking place on both the sides and its thickness will be increasing from the entrance of the pipe as we move away from the inlet of the pipe in the x direction. Now at some distance from the inlet of the pipe, velocity boundary layer will be grow in thickness and they will merge at the center line. So the region from the inlet of the pipe to the point at which the velocity boundary layer grow and meet at the center line of the pipe is called as hydrodynamic entrance region, and the length of this region is called as hydrodynamic entry length. The flow inside this hydrodynamic entrance region is called as hydrodynamically developing flow because the velocity profile is continuously developing within this zone. Similarly, the region beyond the hydrodynamic entry length is called as fully developed region because in this case the velocity profile has fully developed and it does not change as we move away in the x direction, and the velocity profile shape is parabolic. The velocity of the fluid is maximum at the center line and 0 at the top surface and bottom surface and vary from maximum to free stream velocity to the 0 in between. Generally, the maximum velocity is twice of free stream velocity. Now, in case of internal pipe flow, the velocity at the center line is increased than the free stream velocity. Because what happens? Because of this development of velocity boundary layer from both the side, flow area gets reduced. So in order to mass flow to remain constant, velocity is increased. That is why at the center line of this pipe, velocity will always be more than the center line. So this way, because of the no slip condition, the velocity profile is developing in the hydrodynamic entrance region is fully developed in fully developed region, and velocity becomes maximum at the center line of the pipe. Similarly, development of hydrodynamic or velocity boundary layer for fluid flowing through tube will take place in case of turbulent flow. Now in case of turbulent flow, similar phenomena will be observed. That is because of no slip condition, velocity will be zero at the top surface and bottom surface and will be changing from zero at the top surface and bottom surface to the free stream velocity at the center line, and the velocity profile will continuously changing in the hydrodynamic entrance region and will be fully developed in case of fully developed region. However, there are some differences. The development of hydrodynamic or velocity boundary layer in case of turbulent flow, the velocity profile will be quite blunt because of intermixing of particles due to rapid fluctuation. Similarly, the velocity profile in case of fully developed region will not be the parabolic, rather it will be somewhat flatter. Also, the maximum velocity will be function of free stream velocity and Reynolds number value. So we will also get the blunt shape of velocity boundary layer and blunt shape of velocity profiles in case of velocity boundary layer development in turbulent flow. So similar kind of observation are there in case of turbulent flow. Now development of thermal boundary layer TBL for a fluid flowing through the tube. Let us consider the temperature of the fluid is higher than the tube surface temperature. That is, hot fluid is flowing through the cold surface. So let us consider a fluid with free stream velocity u infinity and temperature T infinity is entering into the tube. At the inlet of this tube, the temperature profile will be uniform and constant. But as we move away in the x direction from the inlet of this pipe, the temperature of this fluid in contact with the pipe surface will become equal to the temperature of the pipe surface. That is, temperature of the fluid particle in contact with the surface will be equal to Ts. And because of heat transfer, it will gradually increasing as we move away towards the center line. So the temperature profile will change its shape from uniform shape to somewhat parabolic shape. As we move away further in the x direction from the inlet of the pipe, effect of heat transfer will be penetrating more and more, and the temperature profile will continuously changing. With temperature will be equal to fluid temperature will be equal to surface temperature at the top and bottom surface and will be equal to T infinity at the center line. So because of this no temperature jump condition, a small region in the y direction is developed where temperature gradient is existing, and the thickness of this region is called as thermal boundary layer thickness. So such region is developed on both sides of this tube where temperature gradient is existing, and this region is called as thermal boundary layer. The thermal boundary layer development will take place from both the sides, and the thickness of the thermal boundary layer will grow in size, and they will meet at the center line at some distance x from the inlet of this tube. So the region from the inlet of the tube at which thermal boundary layer is developing and meets at the center line is called as thermal entrance region, and length of this thermal entrance region is called as thermal entry length, represented by Xc suffix Th. The nature of flow in this thermal entry region is called as hydrodynamically developing, the thermally developing flow, because temperature profile in this thermal entrance region is continuously developing and changing. The region beyond the thermal entry length is called as thermally fully developed region, because the non-dimensional temperature profile Ts minus T over Ts minus Tm is constant in this region. However, shape of this temperature profile may vary or change as we move away in the x direction from the entrance region. But this non-dimensional temperature profile will remain constant. So unlike the velocity boundary layer, that is velocity profile, that shape of the temperature profile may vary in the x direction. Okay, so this is very important observation in case of development of thermal boundary layer. The similar phenomena will take place when a fluid with free stream velocity u infinity and temperature T infinity is entering into the tube, and when tube surface temperature is more than the fluid temperature. That is, when the cold fluid is entering into this hot tube, because of no temperature jump condition, temperature of the fluid will be equal to the surface temperature of the pipe at top side and bottom side, and will be equal to the free stream temperature at center line. And this effect will grow because of temperature effect is penetrating more and more as we move towards the center line. So once again, there will be thermal entrance region where temperature profile is continuously varying, and velocity boundary layer from both the sides are merged at the center line. This region, this length is called as thermal entry length, and beyond this thermal entry length, the temperature profile is fully developed. So this way, the development of thermal boundary layer will take place in case of fluid flowing through the tube, either hot or cold. So from this discussion, we can say the reason in which the flow is both hydrodynamically and thermally developed, and thus both the velocity and dimensionless temperature profile Ts minus T over Ts minus Tm remain unchanged, is called fully developed flow. Mathematically, I can define hydrodynamically fully developed flow in which variation of velocity with respect to the direction x is equal to 0, and thermally fully developed flow where the dimensionless temperature profile Ts minus T over Ts minus Tm with respect to x is 0. So when these two conditions are obtained, the flow is called as fully developed flow. Now let us discuss some useful relations. As we have discussed, in case of internal flow, the velocity of the fluid is continuously changing. 0 at the surface to the maximum at the center line. So it is not a proper practice to use free stream velocity for all the calculations. For that purpose, a mean velocity of the fluid is considered for calculating Reynolds number. So in order to define mean velocity, let us first define mass flow rate m dot is equal to rho into um into AC is equal to rho cross sectional area of the pipe is pi by 4 d square. So from this, mean velocity is equal to 4 m dot pi rho d square meter per second, where rho is density of the fluid, AC is cross sectional area pi by 4 d square if it is pipe, and d is inner diameter of flow. Number 2, Reynolds number. Reynolds number is calculated to decide the nature of flow. So in case of internal flow, our Reynolds number will be RED is equal to rho UM over mu is equal to U infinity into LC over nu. For circular pipe, characteristics length LC will be equal to its internal diameter. So RED will be putting the value of UM. Let me correct some notations, otherwise you will get confused. This will be m dot and this will be um. Please do not get confused. So Reynolds number RED will be rho UMLC over mu is equal to UMLC over nu. For circular pipe, LC is equal to D. So Reynolds number will be putting the value of mean velocity UM from this equation, and characteristics length LC is equal to D. On simplification, the expression for RED will be 4m dot over pi d mu. So this way I can calculate Reynolds number in case of internal flow through pipe of diameter d. Then hydrodynamic entry length. Hydrodynamic entry length is the length from the inlet of the pipe up to the point at which velocity boundary layers merge, and within this length velocity profile changes continuously. So for laminar flow, hydrodynamic entry length represented by xc lam is equal to 0.05 into d into RED. And for turbulent flow, hydrodynamic entry length is independent of Reynolds number. It is represented by xc suffix turb is equal to 10d. Similarly, thermal entry length for laminar flow, thermal entry length XETH lamp 0.05 into D into RED into Prandtl number. This parameter is nothing but hydrodynamic entry length XC lamp dot Prandtl number. So this represents the relationship between hydrodynamic entry length and thermal entry length. For turbulent flow, thermal entry length XCTH turbo is equal to 10D. So the hydrodynamic entry length and thermal entry length both are represented by 10T. Then velocity profile in fully developed region, U is equal to UM into twice into 1 minus R over RO whole square, where R is any radial distance from center of pipe and RO is equal to radius of pipe. Further, friction factor. So shear stress at the surface tau is given by Cf into rho U m square by 2, where Cf is called as coefficient of friction. It is given as 16 upon RED, and friction factor F is 4 times of Cf, 64 RED. Next relationship is pressure drop and pumping power. So whenever fluid is flowing through the pipe, because of friction, pressure drop may take place. And in order to make the fluid to flow, this pressure drop has to be increased. For that, pumping power is required. So pressure drop can be calculated as delta P is equal to F into L by D, rho UM square by 2, and pumping power W dot is equal to V dot delta P, where V dot is volume flow rate, can be given as m dot over rho in meter cube per second. Here L is the length of the pipe and D is its diameter. Then heat transfer rate Q. From Newton's law of cooling, the heat transfer rate can be given as h bar As Ts minus Tb, where Tb is mean bulk temperature given as T infinity I plus T infinity O by 2, where T infinity I is fluid inlet temperature and T infinity O is fluid outlet temperature. Now what happens actually in internal flow? Fluid is having two temperatures, inlet fluid temperature and outlet fluid temperature. So in order to calculate the heat transfer rate from the pipe surface to the fluid, the Newton's law of cooling for internal flow is slightly modified. Instead of the fluid temperature, we take mean bulk temperature, that is average of inlet and outlet fluid temperature. So please mind well this expression. Now whenever heat is transferred from the surface to the fluid, its sensible heat will be increasing. Can be given by Q2 is equal to m dot into Cp into T infinity O minus T infinity I, where m dot is mass flow rate and Cp is specific heat of the fluid. Now under steady state condition, what will happen? The rate of heat transfer from the pipe surface to the fluid by convection will be equal to increase in the sensible heat. So Q1 will be equal to Q2. For constant heat flux wall boundary condition, Q2 can also be written as Qs into As is equal to m dot Cp T infinity O minus T infinity I. For heat transfer between pipe surface and fluid at the outlet, Q1 is equal to h bar As into Tso minus T infinity O, where Tso is pipe surface temperature at the outlet and T infinity O is outlet fluid temperature. So all these heat transfer rate equations are used simultaneously to calculate any unknown parameter judiciously. We cannot see all those heat transfer rate equation in isolation. Rather, they are supposed to use in sync. So at the end of this video lecture, you will be able to explain the concept of hydrodynamic or velocity boundary layer in internal flow in forced convection heat transfer. You will be able to explain the concept of thermal boundary layer in internal flow. And finally, you will be able to explain the significance of VBL and TBL in forced convection heat transfer during internal flow. So with this, I come to an end of this video lecture. Thank you for passionate listening. Happy learning.